This is an example of applying the first law to a closed system. We'll start with 1 mole of an ideal gas. We're given the heat capacity, and it's in a piston and cylinder arrangement. We're going to compress the ideal gas from 300 Kelvin and 0.10 megapascals, which is around 1 bar pressure, or is 1 bar pressure, 2.8 megapascals. And we're going to do this isothermally, and the problem asks us to calculate change in internal energy, enthalpy, Q, and the work of expansion and contraction. To do this problem, what we want to do is first specify our system. So this is a drawing of a piston and cylinder. We'll take the gas within the piston and cylinder as our system. Next, we look at the degrees of freedom. Initially, we're at 300 Kelvin, 1/10 of megapascal. The final condition, since it's isothermal, 300 Kelvin, and 0.8 of a megapascal. Since it's a single component system, the phase rule says we only need 2 state variables to completely specify the system, so both states are specified. What we want to do next then is apply the energy balance to this system. Since it's a closed system, no mass transfer in, no mass transfer out, the energy balance simplifies to delta U is equal to Q plus W. And because the system is isothermal, delta U is 0. Delta U is CV delta T for an ideal gas, and that's 0. Next, we want to calculate the work. Well, to calculate the work, the pressure is changing. We're going to use the pressure to gas, so we're assuming it's reversible. We'll go from the initial state to the final state. In order to solve this, we have to relate the pressure to the volume with the ideal gas law, and this is the work of expansion and contraction. So this work then is minus RT, since R and T are constant. The integral dV over V from state 1 to state 2, which is minus RT, the natural log, volume 2 over volume 1. So in order to determine the work, we need the volumes. So we have to go back to the ideal gas law. Isothermal, pressure 1, so gas constant 8.314. I picked units for gas constant, and therefore its value. So we're in megapascals, moles, and Kelvin. 300 Kelvin, 0.1 megapascals. And this gives us the volume per mole, 24,940 cubic centimeters per mole. Same type calculation, of course, for our final conditions. 8.314, it's isothermal, and the pressure is 0.8 megapascals, so the final volume. So now what we want to do is substitute into the expression we obtained by integrating the integral PdV, get the expansion contraction work. And now I'm going to pick R in units of joules per mole per Kelvin. Temperature is 300 Kelvin. I have the log of the final volume over the initial volume. This number, if we look at the significant figures, probably 2 significant figures is justified. I'll put one more down here, but we're only given some of the values to 2 significant figures. Back to the first law. It's isothermal, delta U was 0, so Q is minus W, and therefore Q is minus 5190 joules per mole. Now we get answer, let's go back to the work. This says the work is positive, so we've added work to the system. And this makes sense because we're going from low pressure to higher pressure, so it's a check on what we're doing. If we're adding work but we're keeping an isothermal, then we must be removing heat, or it would not stay isothermal. So again, that's consistent. And the problem asks for delta U, which we already determined was 0. And likewise, delta H is 0, since delta H is Cp delta T.